So I'll just launch right into it. What is cut file BIM? So it's a term that we've invented. I should say that the last few presentations have been very interesting. It's very much the life that I live as well, the same life that these folks are living. I would describe the company that I owned until recently and sold as a very mature user of 3D modeling, parasolid modeling, and so on. We started using it back in around 1998, and by 2003, 100% of our output was 100% modeled. Now, we are the ultimate example of a lonely BIM company. So we're doing $3 million feature stairs and, Hilfiger's global flagship on Fifth Avenue and so on, and everybody around us is working like they're in the dark ages. And that's been very typical. And so the presentation you're about to see is really all about our road to completely dominating the modeling process from the top down, an attempt to completely model an entire building and what it takes to do that. And in fact, not just model the building, but make the building and sell the building. So actually, sorry, so you got that already. The cut file building information model is a model that workers on a job site, CNC programmers, and machine operators can rely on. That's really fundamental to my belief in what a BIM model actually should be. It should be absolutely accurate, and it should include all the information that everybody needs to get the job done. Unfortunately, most participants in the process are using these architectural visualization platforms, essentially what I think of them as, whereas the fabrication design platforms have really a very different focus. Their focus is on generating cut files that operate CNC machines and so on. So at least 75% of a building at this point becomes a cut file. That information is, that 75% is extracted completely out of thin air. I have no statistics to back that up, but jobs that I've worked on recently, that certainly seems to be the case. As an example, the bow in Calgary, the front wall done by Soda, the back wall done by Antimex, the structural steel done by Walters, the washrooms done by us, mechanical done by somebody else, and so on. All of that was 3D modeled. If it fits in the model, it will fit on site, is true, and so as if it don't fit in a model, it won't fit on site. So that's the inherent risk in modeling and trusting the model, is that if the model's no good, it's definitely a garbage in, garbage out situation. So in fact, the fabricator's model is the last line of defense. In this context, a building information model is machine instruction. So drawing has become building. When you're laying down lines on a screen, when you're describing objects on a screen, today you are building the building. It's no longer the case that you're representing the building in a true building information model, you are building the building. Unfortunately, the architect uses architectural design software, the engineer uses the schematic design software that we've seen, fabricators using their trade-specific package in many cases. So you have the Tower of Babel effect, and you have a bunch of people attempting to, manage that with various platforms that notionally integrate all of this data, but they absolutely don't integrate the data to the point that you can extract a cut file in one person's Tower of Babel software from another person's 3D model done in a different platform. So fundamentally, you've got a whole bunch of lonely BIM people, circulating around each other like planets around a sun. And there's no sun. I think that metaphor has gone too far, so we'll move on. So what is really needed, in my opinion, is a single source of truth model that all can make and all can use to generate cut files. And in fact, this whole process already exists. The Airbus A380, for instance, was modeled in CATIA, down to the last nut, bolt, screw, washer, rivet, the little instrument needles inside the dials in the cockpit. Oh, it's all screens now. The LEDs that illuminate the screens, the internal components of those, virtually everything in the entire aircraft designed in CATIA and produced, injection molds made from those files, material bending, material cutting, and so on. So that process exists. People have believed that it's far too expensive to apply to architecture, and I don't believe that that's any longer the case. Many industries have been modeling to cut file level for 20 some odd years at least and more. The CATIA suite of software was developed back in the 80s and it was used to build the Mirage. Now the difference between Now, here's the key thing, though. The difference between a conventional building information model and a cut file building information model is the degree of completeness. So the degree of completeness of a cut file BIM is very high, A, and B, it requires expert input to create. So all of the folks that you've seen up here earlier today, all of their input is required on the cranes, on the what's feasible in terms of connections, what's feasible in terms of piping, what's feasible in terms of airflow, of insulation, insulation, everything else. You need all of that information before you can create a fully complete cut file level BIM. That's obviously very challenging. And what exactly is complete? Complete is actually complete enough that there is no decision making required in the field whatsoever and no rework whatsoever required. That would be a truly complete building information model. So interestingly, at this point in time, probably the only way to get there is to entirely fabricate everything in that building in one plant in accordance with one model. And that's very much what happens in the aircraft industry. So in Toulouse, when the Airbus A380 goes together, it is being assembled from components that have all been coordinated by one model and all made by suppliers using the same software. So now I think most of you will have figured out by now that unless you pitch work done by Alan Partridge, you won't go far in this organization. So I'm about to do that. And I also apologize to people who have seen this already. But it is it's still one of the better examples of this type of work. So the Shaw Auditorium in Edmonton, Alberta, we did the mandatory 3D laser scan using the Leica system. And then in order to deal with the sloppy geometry of this multifaceted space, we actually designed a space frame that fit completely independently of that space. And to that, all of the interior finish components were applied. And we shipped to the site ceiling panels with the ducts in them, with the speakers in them, with cutouts for the sprinkler heads in them, the diffusers for the heating, ventilation, and air conditioning. Absolutely everything that you could see in this room, other than the carpet tiles and the electronics in the rack, were in the model, fabricated off-site, and installed in accordance with model data. And I'm not exaggerating to say that the fit and finish of this interior was absolutely perfect. We had a gasketing system that would go between these panels that allowed for a variation from 1/2 inch down to 1/4 inch with a mean of 3/8, and really there were hardly any that weren't 3/8 anywhere in the entire interior. So a couple of years later, actually I didn't put a date on this, this job started in 2010, we were awarded an $18 million contract to supply about 40,000 square feet of washrooms on a modular basis for the bow. And so we proceeded to model these things. And you see here a 100%, well, let's call it 99% complete model of one of these washroom modules as seen from the outside. And this model, every single part of this model has the material properties, so density, volume, et cetera, et cetera. Even the toilets, we didn't have a complete model for them, and they're made of ceramic, and they have all kinds of weird hollow voids in them. So what we did was we actually put them on a scale and then moved a dowel back and forth underneath them until we found their center of gravity, and then put them into the model with those properties as kind of a separate menu of properties associated with that object. You see here that those little triangular brackets, for instance, that go between the studs and that horizontal tube, that is the cut file for that component. In that little baggage compartment latch that holds the door shut, the access panel shut, that assembly came to us with the little springs in it and the bevel on the end of the pawl and the component that it locks to, similarly articulated so that when we hinge that whole panel, it would actually work the pawl and the spring, and you could actually see how far it had to move in order to engage and so on. You see there that yellow arrow, the heads could be larger. It shows the pipe fitting inside the collar. The collar's been modeled. It's got a little annular ring inside it. It's got a tolerance envelope around it. So when you build the plumbing of this unit out of these components, you then get the length of the pipe, and it goes into your bill of materials. This shows the ceiling. In the ceiling, we took advantage of the fact that we had complete control of this process, and we slammed 2 feet, a 2-foot thick layer of ducts and indirect lighting troughs and all kinds of stuff into a 5.5-inch thick sheet metal sandwich that cost us about $1,800 to make. And to have put all that stuff together in the individual fabricator shops, you know, everything from sprinklers to this, that, and the other, you literally add a zero to that. So we were able to make these ceiling assemblies for 1/10 the cost out of sheet metal that it would have cost to make them all out of discrete components in multiple trades shops. So this is a photograph of one of the units that we fabricated, photographed in our plant before it shipped. Sprinklers tested, the tubes in the sockets, the plumbing pressure tested, even the drains pressure tested. And this shows one of the units rising on the gravity neutral platform. Here it is moving on air bearings to its finished location. And here it is in place in its virtual form. There it is in its actual form. I'll just do this a couple of times. If you look at any part of those two views, you see that there's literally no deviation whatsoever. So that's an example of something that's been 100% modeled, all 9 trades fabricated in one facility, shipped to the site, and integrated at the site. And the labor cost differences here in this, you know, Calgary labor market context was enormous. So the key to achieving these workable, realistic, this workable and realistic degree of completeness can be summed up, and this is sort of like the, you know, location, location, location with real estate. It's detail the building, detail the components, and detail the production fixtures. And I include a crane as an example of a production fixture. So it's absolutely essential that anything that you are going to put into one of these very complete models, that the process that will be used to create it is as perfectly understood as possible. And that does mean bringing in experts to provide you with that information. So here's an approach to that, which I was very fortunate to have the opportunity to create. We created what we called the recording studio for architects. And this is where we built our single source of truth models. And we had a very interesting workflow. So we had a group who just simply found components and palletized them so that they would go nicely into the model and locate appropriately. We had a group that created sub-assemblies and a group that created assemblies, master assemblies. And this really is actually the file structure that you see over on the left or right-hand side of your modeling software screen. What you see is the file structure, and we organized our facility, our design facility, around the file structure of 3D models. And that worked extremely well. When you were short of people to do one phase, you could draw them from another phase, and it'd be quite easy to understand how that labor mobility within the facility worked in terms of capacity. So I sold that company to Walters, actually, I guess one of Canada's, or if not Canada's, leading structural steel fabricator. They liked the way we worked, and they bought the company. And so then I had to do the mandatory year off, the non-compete year. I went to Shop Construction in New York City and became their in-house modular constructability guy. And this is at the time that they were designing B2. We're in the tail end of the process of designing B2, the tallest modular building under construction anywhere in the world right now, and so on. And in fact, it had become apparent at a relatively early phase to the people at Shop that the project might end up, with some issues. And so we embarked with a team there on a project to develop an alternate way of building buildings like that addressed many of those issues. So it was very proactive of them, and I congratulate them for that, and I was obviously very grateful for the opportunity. So while we developed a bunch of projects that are under construction right now, I think the most important thing that came out of it was what I'm about to show you. So, whoa, back up one. So first of all, we had a great engineer on board, Arup, who are a terrific firm. And the first thing we did was we went through the whole, we created essentially a hypothetical building, which we actually had a client for in Chicago, but we looked at that project as what we called tip mod, so typical modular. We said, if this is a building substantially of a type that we see going up in Toronto, going up in Vancouver, going up in San Francisco, so we're going to take this project as an example and we're going to work it through. So the first thing we looked at was the structural frame. Obviously, these modular buildings all have, in our conception, they have structural steel frames. We started looking at what the real loads were everywhere in the building and what was really required to support them. The next thing, of course, was to feed shops experience in the design of very successful residential buildings into this process and come up with, so essentially what we ended up with was a chart of all our restrictions. We really knew what we could and could not do, what we had to deliver and what we didn't have to deliver. Whoa. And then the thing that really came out of this, and it's strange that it's something so ordinary and so prosaic, but we found out that the separate brace frame that just about everybody is implementing in these types of buildings, or brace structure, is really one of the biggest problems in implementing a structure like this. And it's so fascinating how the previous presentations today have, every one of them touched somehow on the issues that we all face. Essentially, that separate brace frame is this horror show of two trades working side by side. So if you've got a modular building erector and you've got a brace frame erector, and they're supposed to move, erect side by side, and they have different degrees of settlement, and they have different levels of accuracy, and they have tolerances, envelopes all around them, and so on, that's a disaster. And if the core, if you're putting up a structural concrete core next to a stack of steel boxes, then the problem only becomes worse. So we settled on something that is actually quite, I hope you like it. It's simple, but it is radically different. And so then I left. I was leaving Toronto at 5 o'clock in the morning on Monday, and returning home at 10 o'clock on Friday, and the commute was a little rough. And so I decided to return home, and in fact, the non-compete was up and so on. So we launched a new company, and this company is focusing on developing this modular solution. And that, by the way, is a picture of my office. So we all know that industrializing the building process provides all kinds of benefits. I think that's one of the things that unites us in this group. And it really comes down to, would you rather work here, the horror show of a typical job site, the way nobody seems to be able to stop running them like that, or would you rather work in an environment like this? And this is a picture of what is effectively our prototype shop. And we are actually producing, I would describe as architecturally sophisticated work. And, but it's, it's a nice place to work. We keep it clean, we keep it well organized. And, I've got folks working for me that are, past 60 years old, very, very experienced people. They can make anything, we joke that they can make anything with nothing. And to be able to attract workers like that is actually hugely beneficial to your organization. And, if they have to be, wading through somebody else's offcuts on the 30th floor in January, it's a lot harder to attract folks like that. So done right, volumetric modular building is definitely the most productive construction method. I don't think any of us would debate that. And we find that, comparing the work on a unionized job site in New York City to our shop in Toronto, the difference is 4 to 8 times in terms of cost per unit of output than the same job done in our facility. And if you're using something like this beautiful Voortman beam line, compared to somebody using an oxyacetylene torch to cut a beam to length and then drill holes in it with a magnetic base drill while they're kneeling on the ground in a blizzard, the difference is 20 plus times. And by the way, things like, I had a sign fabricating project, it would be now 35 years ago, where I cut out a beautiful sign for somebody using a jigsaw out of 1/4-inch stainless plate. And it was 2 feet wide and 20 feet long. And I was cutting letters out, and that's how you did it in those days. And it took probably 3 weeks or something like that, and a horrible stack of blades. And the same job today would take 2 hours and cost $300. Whoa, doesn't respond instantly. So completing modules off-site is a good idea, but volumetric modular construction seems to hit a glass ceiling at about 5 floors. And so there's a vast industry, a ton of competitors in the single-family dwelling modular market. And then there's an almost equally vast number of people building the types of buildings that you see in these images here. So we see the biggest challenge in the business, and this has been borne out by the experience at B2, the biggest challenge in the modular business, and so that becomes the biggest challenge to creating a top-down single source of truth model that allows you to create an entire building and manufacture the whole thing off-site, ship it to the site, and plug it together like Lego. The biggest problem is inherent in all tall construction. goes again slow. Oh no, did it? So there are 5 major challenges to tall modular construction. So number 1 is accumulating tolerances. That's really troubling everybody. Where do you point this thing so it works? There we go. Number 2 is a separate brace frame. The separate brace frame, we can elucidate all the issues, but when you think about it, you've got this pocket going up through the building that you can't waterproof. It's ascending at a different rate. It blocks the halo that lifts the modules. You can't get safely by it. Its diagonals change, so your ramps are moving around. It has a huge number of issues. The next is iterative re-rigging. So you're trying to put up 20, 30 modules a day, but you're taking half a human lifetime to adjust the rigging on every module as you're going up. Next one is the work outside or under modules. It's really from, in terms of OSHA or in Canada, our regulations, it's totally unacceptable to have men under a load, yet it's happening all the time in the modular industry. And last is the damage of the modules banging into each other, especially in the facade areas when you're putting them up. So it's a great idea, but people are having trouble doing it. So what we've done is we've basically, riffing off the ISO corner that you see on ocean freight containers, we've developed a specialized connector that performs many of the roles that the ISO connector performs, but it also provides vertical tension capacity, anchoring points, and a whole bunch of features that you're going to see. But the most important thing that it provides is a means of making a perfectly accurate module. So you space those ISO connectors accurately in space, you join them with lengths of material, the cut length of which is completely irrelevant, and you end up with a perfect box. And you can easily imagine how modules, pipe rack modules, for instance, or some kind of industrial module where the ducts, the pipes, and so on, when you position the modules end to end, are perfectly located for the welds, for the bolts, or whatever, is a very different paradigm than making up the modules in a plant, bringing it to the site, and still spending hours trying to bang the stuff into alignment before you join it. So there's 10 key features to the system. Repeatable design and engineering process. So you get to reuse that intellectual labor. Easy fabrication of accurate modules. It's got to be easy. Stackable load-bearing modules, so you don't have to erect a separate brace tower or brace structure. Thin walls, so you got lots of gross floor area. You're not using it all up in ancillary structure. You got to be able to rig, level, hoist, and release the modules quickly. You got to be able to connect them from inside, so folks aren't having to meander around on the outside and use swing stages and everything. And this really, by the way, once you get past 7 floors, obviously you're not using cherry pickers from the ground. Easy surveying and elevation control. Easy rigging of safety barriers. This is strangely an afterthought for a lot of people. And facades and balconies that connect easily. You don't have a lot of issues banging that stuff into place. And dependable rain protection during building assembly, which area is not adequately described in what you're about to see, because we're still working on it. Which isn't to say it isn't possible. So the tolerance issues, they really start to build up after 5 to 7 floors. It's killing everybody. We say by solving tall, you solve it all. So obviously, if you can build a tall building, you can build shorter buildings. They're not an issue. So at the heart is this connector assembly. You can see on the right there an image of a building, and it shows how the connector assembly can be equipped with a great variety of columns as it goes up. So you design a column around the actual loads that exist in the building, where the connector goes. The connectors are designed using this same aerospace software. This happens to be the model showing actually the thickness throughout the object, because this is related to cooling rate in the casting process and so on. There's all kinds of features concentrated in these blocks, so basically anything that would require machining, precision, drilling, threading, anything all goes in the block, and the members in between them are just dumb members. They can have angle cuts, they can be too short, they can be too long. You don't have to drill any holes in them. There's a whole bunch of different connectors to deal with the great variety of conditions in a building. So here you go, you take your load diagram, you pick the connector type that fits. You have this enormous variety, so you can definitely find one that is using material that you like to work with, even. The connector is never the weak link in the chain, so they've threw a few extra pounds on there, so you don't have to have tons of different ones. And this is ultimately the result. So you take the brace frame out, you collapse the structure on either side, and you eliminate a huge amount of wasted space, and this is really the biggest benefit, you actually multiply the structure. So you see here, by the way, that we can jam a 400 pound per foot column into a 10-inch wall with a few little bumps at the corner, and that's it. So, by the way, in comparison to this hotel, when you look at the amount of concrete in the lobby, it's extraordinary. So, and this is the the bundle of sticks concept, the wicker furniture concept. Obviously, an individual piece of wicker is pretty flimsy, but when you bundle a whole bunch of it together and tie it into a bundle, it becomes very strong. And this is the other key feature, is that the modules have to be fabricated so that no part of the module goes beyond the mate line and prevents close contact, well, really slip critical connection vertically between the structural members. So it's, again, this is where the tolerance control becomes paramount. I won't bother to read this list, but there are a ton of benefits to this. Take my word for it. And here's an additional very important point, is that the other thing that you do when you eliminate the brace frame is now you can have structural continuity through the entire floor, through an entire floor of one of these towers. So now you can concentrate the diagonal bracing in the stair towers, the elevator shafts, and so on, and it'll act through the whole building. So if you can make an accurate module, and if you can join them together tightly, so that all the structure acts together, then suddenly you can concentrate this diagonal bracing function into some isolated areas. It doesn't have to be ubiquitous throughout the structure. So the effect of all of this improvement in the approach is to dramatically reduce the amount of diagonal bracing required. So you see here, this is the lateral framing system. It occurs in the party walls, basically, of the units, and it can be sort of 1 every 3 or 4 units. And the longitudinal framing in the upper parts of the building, it can be in the stairwells and elevator shafts. In the lower parts of the building, yes, you need some more, and especially in a seismic zone. But in any case, you need far less than you otherwise would. Of course, with beautiful, accurate accessory connection points, we call them, around the face of the module, the whole business of connecting balconies and so on becomes dramatically simpler. It means you can implement these thermally broken balconies that everybody wants. You can fabricate the balconies in one plant, deliver modules to site and bolt them together at the site and then raise them. You could bolt them on after you raise them. You could bolt them on in the plant. But the bottom line is they can be made by 2 different people with specialized materials, and they can be readily connected without a bunch of little shoes and brackets and plates and slots and whatever to make that connection happen. This shows as the building rises, the hallways are going in after a level of modules is stacked. You can walk down the hallway, you get to the connection points, you can see there in the bottom right, that are behind accessory panels in the hallway. This is out towards the outer wall, the other connection point. You can see that you've got a nice grouping there of 8 grade 8 bolts, each of which is going to have something in the order of 30 kilopounds of tension capacity. So really in a building of 10 or 15 floors, you actually only need about half of these. And of course, you can make up different suites by grouping different modules. And again, back to this idea of an all-encompassing, do-it-all in the factory approach. Of course, these modules can be shipped with the kitchen cabinets, with the bathrooms, with the tiles, with everything already installed in them. So you don't have any coordination issues at all, notionally. And in fact, you can cut all the material with CNC machines and install it all, with folks rolling around under a roof. It's a very different approach, and I think the benefits are self-evident. We don't want to, and by the way, I should have apologized in advance after having seen such beautiful examples of architecture today. I know that our model, our model building, let's call it, is sorely lacking. I want to assure you that we are not condemning for all time all architects to build, hideous towers. And in fact, the next phase in the development of this system is the ability to implement a variety of building typologies and provide the freedom to the architect that they currently have. Is somebody going to clap at this? Here we're showing modules stacked to form stair towers, elevator shafts. Here we've got the hallways as MEP carriers. So you cast these things upside down. You assemble the pipes, if you will, like this. Fellows working at a bench like this, assembling the pipe. Flip it over and drop it into place. So this gets us, this system, should we prove successful in implementing it, gets us to the point where 95% of the work of putting a building together can be done in a plant. And that, we believe that's about as high as you can get. I mean, you're never going to get to 100%, obviously, because you have to stack the units at the site and you have to connect them together. And there's compromises in every approach. The object here has been to try to reduce the amount of work done on the site to the absolute bare minimum. So this whole issue, accurate equals cheap. People think accurate is expensive. People think that all this planning is expensive. People think that this approach is expensive. A remarkable number of people think that. In my opinion, and this is based on more than 30 years making some complicated stuff, the cheapest way to build something is to build it accurately. So we've put a lot of thought into this area. As a matter of fact, it underlies the whole approach. So cheap in the case of a fabricator means not having to invest an enormous amount in equipment. And so we've come up with this idea of what we call the Vectorjig. So this is a space frame. It's made out of laser cut plate. As you'll see, we have one partially fabricated now. The laser technology that we've been talking about is used to align something like this very much in the way that machines for industrial robotic applications and so on are aligned. There's laser leveling systems widely available now, used by the machine tool industry, that are available on a daily rental basis, and they can measure to an accuracy of 2/10,000ths of an inch in 100 feet. And these are not uncommon, surprisingly. And in fact, you can generate data from those systems that will cause the heads of milling machines, of precision machines, to rise and fall and compensate for the inaccuracy that the machine has measured. So you can actually have a bent machine and produce square parts. The jig has a whole series of pins. The pins are deployed in order to control the position of the material, make sure that no component ever exceeds the mate line. And the jig can open to release the modules. You can, if you had enough of the jigs and you wanted to spend the money on that, and we think that actually they're going to be relatively inexpensive, you can complete the modules in the jig. So as you apply the wall board, the floor board, the ceiling board, any tension bracing you want to put on it, you actually lock in this perfectly square shape. There's an image of the prototype that we're working on in the plant. That picture was taken yesterday. And you can see the laser cut plate with these pins fitting into it and so on. And this shows a row of the pins activated by a rack so that they can rotate with the hydraulic ram operating the rack will rotate the pins and perform the clamping action. So we're foreseeing a jig where, for somebody who wants to invest the money in it, the rate at which the jig can be loaded, the welding can be conducted, and the part released will be reduced to minutes. So here's this issue of hoisting. The centers of gravity of these things flip all over the place, and you can't say, well, you know what, I'm only going to hoist the ones on Wednesday that have the center of gravity here, and then on Thursday I'll move the rig around and do it then, and so on. On any given floor, you are going to have a wide variety of centers of gravity, no matter what you do. The only building that wouldn't have this would be, I don't know, a military barracks or something like that. But any kind of an attractive residential building is going to have this setup. So you can't be, picking a module up, seeing how it hangs, putting it back down, adjusting the rigging, picking it up again, seeing how it hangs, putting down the rigging again. You want to know exactly how it's going to hang. A. And B, you want to be able to connect and disconnect quickly. So the current state of the art, believe it or not, is to, bolt a fitting to the thing, put in a shackle, tighten a screw, and so on. We've developed a quick connect and disconnect fitting along the lines or inspired by those that they use for ISO containers and so on. So this literally clicks in place in 2 seconds, releases in 2 seconds, but almost more importantly, provides a very accurate anchor point so that, as you see here, the halo frame, if you've designed these things in a single source of truth, parasolid modeling platform, and you know the weight of every stud and every screw and every sheet of wallboard and every pipe, you can set up this halo in accordance with the center of gravity data, and this thing will pick and fly level out of the box. And that's exactly what we were able to achieve, by the way, on the bow. We were able to direct the crew at the site exactly where to put the thing on the platform, and there were bars and holes and pins and so on that located it and achieved that. And of course, the blocks have, of course, a nice accurate hole, and there's a tapered pin and so on that it sits down on to drift it into its final location. Now here, I've got 9 minutes and 14 seconds, so we're not doing too bad because we're gonna kill this. You got here, so just think about this, plus or minus a 1/16, 20 modules. It can be 1.25 inches too high or 1.25 inches too low. That's 2.5 inches. Who would tolerate the outer wall of their building having a 2.5-inch bump in it? Or who would tolerate, the roof of their building have 2.5-inch bumps here and there? Of course, nobody would. What happens in conventional concrete construction or conventional steel construction, the building is monitored as it goes up, and adjustment is done along the way to bring it into tolerance. But if you're trying to prefabricate modules in a plant and erect them, in the field, you really can't do that. You don't. A lot of your opportunities for adjustment are lost. So this plus-minus tolerance envelope idea doesn't work for modular construction. You have to have a +0 minus something tolerance envelope. So you think of that jig, if you're going to make a module that's 10 feet wide by 10 feet high, you will actually always set everything at 9 foot 11 and 15/16 by 9 foot 11 and 15/16, so that for sure nothing is going to get too high. Then you monitor it as you go up with one of these precision leveling systems, which we have adapted to fit on the safety rail posts. And the software, you see in the bottom center there, this slide, the text is a little too small, but in the center there, that's the type of output you get from a dynamic measuring system. So you've got feedback coming from your little receivers that are receiving the laser light, and it goes into your laptop by a wireless connection, and then it outputs a little map that shows you how far off you are from the model data. And then in the bottom right, it shows you how to place shims in order to deal with that. So let's say that after 5 floors, you've got one corner of the building that's dropping, it's a 16th low, and I mean, I truthfully believe that we will be able to hold that sort of tolerance. Then you can slip in one piece of 16 gauge sheet metal as big as the top of the connector and keep going. So that becomes the process. Into this section of facade damage, pretty easy to see. You got a 12-ton module with stone floors and stone countertops, cast iron pipes and everything else. And so there's kind of this is a fellow named Robert Francis, by the way, who is the expert on modular construction, formerly at Balfour Beatty and now at Skanska in the UK. Really is a very strong advocate of this idea of a facade cassette. And he just believes that the facade should be made in a plant, brought to the modular plant, hung on the module, hoisted, and that's it. And nobody ever goes out on the outside of the building with a swing stage. You don't have to have any of these manipulators or any of that stuff. It's all done in the plant. It's actually been very hard to achieve. So the solution that we came up with here, this is a gasket. Unfortunately, in this slide, it may be a little bit hard to see, but you'll see an extrusion, twin mating sawtoothed extrusions that are indexable once the unit has been placed. So you reach into a cavity in the end of the module, you index these things out, you close up the gap, and you're done. I'm going to show some of the details in perspective views. And of course, we've applied for patents for all this stuff, and we went for the PCT version, which covers us in well over 100 countries, very few of whom actually respect patent treaties. And this is the services element to the pitch. And I apologize if this does seem like a pitch, but it is. So that's why it sounds like one. It was basically created as a pitch to contractors and developers and so on. So obviously we believe that we would add some value to the building design process by looking at the way the building has been designed and by reinterpreting it to some extent to make it more perfect for modular execution. We don't want to, put it this way, have 100% control over the architect at all. Our goal, in fact, is to appeal to them as somebody that can liberate them to some extent from maybe the more pedestrian aspects of the building process. And so this is where it's all headed. This is headed towards a catalog of components which are predetermined to be compatible, are geometrically accurate, and that can be assembled to create an entire building. So a building designer, hopefully in the near future, will be able to select their HVAC system, their curtain wall system, their cable entry facility, their elevators, etc., their parapet, roof garden, exercise area, their swimming pool from a catalog, and you'll be able to plug it together at the site. This is our little shop. We've got 9,000 square feet, which is essentially an architectural product prototyping facility, I would say. As a result of the experiences that we've had in modular, we also believe that we would likely be useful to advise somebody who is planning on setting up a modular plant exactly how to do it. And that's it. So I got 3 minutes and 28 seconds to take questions, unless you want to recover this time.
I just have a question with a two-part. Part number one, your system, your modular system passed the structural building code, National Structural Building Code of Canada. And if it passed that, what kind of software is you going to use in order to determine the structure side of your approach?
Yeah, the building design process doesn't really work like that, like that the building code approves the building. So pretty well any building, the drawings are created, an engineer reviews the drawings and determines the sufficiency of the engineering approach and then puts their stamp on it. The architect determines all of the issues related to means of egress and also, of course, the programming of the building and the appearance, and puts their stamp on the drawings. And then the buildings go in for a permit, and basically at that point, the architect's stamp and the engineer's stamp are the assurances that the people providing the building permit have that the building is sufficient. So it's up to the professionals, the consultants, to determine that the building conforms. But certainly the basic scheme that we have developed has been through the 3-hour fire rating and progressive collapse studies and all that stuff appropriate to Chicago and similar things for New York. So, the basis of design, let's call it, has been through that sort of an approval process. But are we there are we at the point where you could select from our catalog and you wouldn't have to stamp it? Absolutely not.
I want to congratulate you for the work you're doing. It's incredible. Two questions. One is, being so close to the manufacturing side more than the construction side, how familiar or how much have you implemented Lean or Six Sigma methodologies for everything, the whole operation, not just shop process, but because you look at it holistically, perhaps these methodologies for efficiency and quality can be applied holistically as well?
Yeah, that's absolutely a part of our whole approach. So, notionally, as so many people have heard, in the automotive industry, for instance, these days, they measure defects per 100 cars. And, it's not uncommon for the level to be under 10 per 100 cars. So that means, 90 some odd cars are going out with no defects at all, and 7 or 8 have one defect. And these defects are extraordinarily minor. Might be the measurement of the gap around a door or something like that being slightly out, or a tiny paint defect or chrome defect or something. So Certainly our approach has been shipping something defective to the site is insane. Why would you do that? If it's going to cost you $10,000 to fix it at the site and it would have cost you $50 to see it and $100 to fix it. So absolutely, the whole Six Sigma idea, that whole methodology, all of that, Toyota manufacturing system stuff, I worship that stuff. That's where all of this comes from. Yeah. All right, thank you.